Good evening, everyone, and welcome to Mastering Direct Placement Restorative Materials. I'm Dr. John Camisi, general dentist practicing in Ithaca, New York, and welcome on this very beautiful spring evening. I'm glad you have the time to meet with me tonight. For the next hour or thereabouts, we're going to talk a lot about composite materials. We've been using some type of composite material for more than 50 years. It's become the routine material used for the majority of all of our direct restorative procedures in dentistry. But sometimes, when things become routine, we can forget the basics of what that material can or cannot do. So tonight we're going to review the makeup of this remarkable material and why it's certainly an important thing for us to do and use. Composites are composed of a resin matrix and, of course, a filler material of some type. Coupling agents are also used to aid in the adherence of the resin to the filler material. Next, there is an activation system. This is what starts the curing process. Plasticizers are used to increase the plasticity or fluidity of the material. You know, that's the feel, the texture, and handling properties of the material. Understanding that the monomers, when activated, create the polymers that become our final restorative material as they congeal and basically solidify around all of the filler materials. And as time has progressed, different types and combinations of monomers have been mixed to create copolymer materials that enhance our materials. And finally, as our understanding of composite science has evolved and the research involved with attempting to improve these materials has led to the utilization of cross-linked monomers that create long chains, which significantly improve the strength of our composites today. It is in this conversion of the monomers to polymers that enables the composites to be composites. And how this conversion occurs is critical in how the material will act over the course of time and its use. It's interesting to note that the independent work of Bowen in the discovery of bis-GMA and Bonnecourt with his work with acid etching of the tooth structure to enhance the enamel bonding process is what started us on the track for using composite restorative materials today. As materials were initially created and used, they, of course, it had the chemical base catalyst material mix that all of us used back in the early 80s and when I was in dental school. Eventually, over time, this evolved into light-cured materials and eventually into microfilled materials that were introduced in the late 1970s. It's amazing to think that it took until that time period, or it was in the 1970s, that these materials became apparent. But let's quickly talk about polymerization. For both light-cured and self-cured materials, this consists of three phases: initiation, propagation, and termination. The oxygen-inhibited layer is the unpolymerized tacky layer that forms on the surface of the composite when oxygen binds to the monomer radicals, which stops or, in this case, terminates the polymerization process before it completes. And if this is less than a few microns, it can be polymerized further with the addition of more material on top of it, hence the continued ability to place new material on old material. The resin material basically is bis-GMA, which is the base of the composite. And then we add diluents, I never get that word right, but someday I will, diluents into it to basically increase the flow and handling or provide cross-linkage to improve the strength of the composites. And these materials are the methyl methacrylate, the bisphenol dimethacrylate, the bis-DMA, the urethane dimethacrylate, the UDMA. And of course, we have the cross-link agents, which are the TEG-DMA and the EG-DMA. And these are what can create our monomers and our resin materials. And then you have the coupling agents that are present. They improve the adherence of the resin to the filler material surfaces that we add into the resin. These are chemically coated filler surfaces to increase the strength, and these are silanes particularly. However, with our silanes there are problems that can occur. They age pretty quickly and they are very water sensitive. Some of the common silane agents are the vinyl triethioxy silanes and the methacryl oxypropenyl trimethoxysilanes. Additionally, we now have photoinitiator systems that are incorporated into what we do. They absorb the light and transfer the energy to the co-initiator molecules to create these free radicals. And the co-initiators do not necessarily absorb light directly, but participate in the creation of the reactive molecules. Photoinitiator systems such as the camphoquinones require a co-initiator such as an amine to be an effective photoinitiator system. And then there are photoinitiators like the trimethylbenzoylphosphine, the TPOs, which do not require a photoinitiator at all to be an efficient photoinitiator system. The camphoquinone is polymerized basically in a range of wavelength between 380 to 510 nanometers with a peak area at 465. The PPDs are photoinitiated between 330 and 490 nanometers with a peak range in the 390 area. And the TPOs, which are initiated between 350 and 430 with a peak area at 375. Notice that the camphoquinone, the CQ on the lower left, is very, very yellow, while the PPD and the TPO are not. And these agents come in very handy in the various mixings for our photochemical catalysts in our materials today. The highest absorption rate for both the PPD and the TPO is about 400 nanometers as compared to the CQ, which is 465. So this becomes very interesting, especially depending on the light that you will use in the curing of your composites. And we'll talk a little bit about the unique aspects there and why we need to look at this closely. In a paper by Elides, Vats, and Elides here, it demonstrates, interestingly enough, that the CQ and PPD, when they're mixed together, act synergistically to increase monomer conversion to the polymer and reduces the concentration of the photosensitized agent and hence the yellow color associated with CQ. So this is another way that our science has continually evolved to improve our materials. We identify a problem and they work to solve it. That's what makes what we do so fabulous. Curing lights, of course, we have several different types. We have had in the past pack lights. We have low power LEDs, high power LEDs, and of course our halogen lights. And on the lower left hand side you see the various peaks of their wavelengths and their spectrum that all of the various lights that have been used or are currently being used exhibit. And then you compare them to the photoinitiators of TPO, PPD, and CQ, and you see that we can, with the wrong type of light and the wrong type of photoinitiator, have difficulties in initiating the chemical cure of our composites if we're not too careful. So this is where some of the industry has had to look at this very, very closely, and now there is a standard that most of our composites are typically going to be cured with our LEDs quite exquisitely. But there are some interesting agents out there and some different light systems out there that include a variable wavelength or various chips in there to give a broader spectrum. So this way, all of our different potential composite photoinitiators can be managed and dealt with. This paper by Price looks at the irradiance or the beam homogeneity of 4 light-emitting diodes. And as you see in the upper right corner, the various intensity of various lights that are present there. When they're very close up, the light is very intense. But as you go down that chart, you can see how the light becomes more and more and more diffuse. And that's because as distance goes by, the light intensity decreases. Dr. Byung-Sur, in his book Principles of Adhesive Dentistry, points out that many practitioners would like to reduce the chair time spent on curing composites. To do this, they would need to wring every last photon out of their curing lights. And a number of manufacturers have introduced turbo tips or power probes to help achieve this. These certainly do this at the tip. And if the tip of your light is directly placed on the target, the restorative composite that you've placed, you will find that unless it's on there, you're going to find that the physics of constant radiance theorem and classic optics show that the intensity of the light will decrease more rapidly as the distance of the probe tip from the target increases because light diverges faster. Dr. Sur states that the light intensity decreases in a linear relationship as the distance from the tip to the object increases. And as we look at the top left diagram with the light probe onto the tooth and the preparation, and sometimes how far away you and I may find that we're holding that light tip away, can really create a problem in the curing of our composites. You'll find that you may be, as I like to call, be creating the proverbial Tootsie Roll pop, in which the composite is crunchy, solid on the outside, but chewy on the inside, which leads to sensitivity, which leads to early fatigue and failure of our composites, etc. In this study by Price, they looked at these 4 lights, fusion, blue phase, demi, and magma, and found that over distances that the fusion light maintained its integrity for a longer time period and a greater distance than any of the others. And that's really very, very important because as you hold your light further and further away, if you don't have good intensity and ability of that light to photochemically cure, you are going to have a problem. So I've been doing some in-office testing over the course of time, and this is one of the slides that I show in my lectures when I'm on the road, and I use a SDI radiometer, which is a really nice light test because you can test both your halogens and all of your LED lights very, very effectively. And here I'm using 3 different lights that we have in the office. I have a fusion on the left, a radii plus in the middle, and one of the new demis on the right-hand side. And you can see that they all, with the tip directly on the radiometer, give us very good milliwatts per centimeter squared of output. But as you increase the distance, as Dr. Sur explained, as I explained a few moments ago, at 3 millimeters distance, you've lost intensity already. And the fusion still holds a pretty good intensity and amount of light and energy being provided. The radii plus is doing a good job, but it's interesting that the demi is beginning to lose intensity. And as you continue to expand upon this and increase the distance from the aperture by 7 millimeters, we're seeing that we're still getting further energy loss. And as you think about it, when you have a matrix band around it and you're aiming sometimes to the very base of your preparation, there could be 6 to 8 millimeters of distance. Are you sure that your light is transmitting enough energy to get down into it? If you don't know for sure, you may be creating problems that you never even imagined. You were blaming your composite, or you were blaming something else, maybe your adhesive system. But maybe it's your light, maybe it's your technique. Because at 12 millimeters distance, which is an absolute ridiculous length, we lose even more energy. But it is a problem in your deeper preparations and how close to the tooth that you hold your light source. So keep this in mind as you go through your days ahead. The more that you understand that the light intensity and the ability of your light to really give good energy to the composite is not going to allow the overall activation system a chance to do its job deep down into the preparation, which is also why if you're not using a bulk material, don't cure more than 2 millimeters at a time. And if you are using a bulk fill material, remember that you want to cure it 4 millimeters at a time, because otherwise the physical properties and the energy able to cure the material is going to be problematic, and you're going to have exquisite failures. And in my work right now, the Fusion light by Dentlight is certainly one of my favorites. It has a very, very nice output, good energy. It also has a violet light head to cure those materials, if you should have them, that will be curing at a lower wavelength initiator, such as the TPOs. And it's multi-versatile and has additional attachments that you can use with it. So check into Dentlight. I think it's something that you'd be happy that you did. So the takeaway from this section of the discussion this evening is that you need to check your light with a digital radiometer every single day. If you're using a radiometer that just gives you several blips of light on it, do you really know what each one of those lights on your indicator mean? Do you really understand if 1, 2, 3, 4 lights that light up when you place it on the aperture for the radiometer really mean anything at all? So you really need something like a SDI radiometer. It's relatively inexpensive and incredible use. We test our lights every day to make sure that something isn't wrong, because even though your light is lighting doesn't mean that it has any energy, especially with our LED lights, so that's really important. As you increase the distance from the bottom of the preparation or from the tooth, you do have to increase time. And as you increase time, unfortunately, though, you are also going to increase heat, because every light source that we use does, unfortunately, generate heat. And if you've never seen that, put a little composite on your thumb and then take your LED light, cure that composite. Watch how you go, ouch. It's really very remarkable to me. The intensity of that heat that generates and builds up in there when you're curing a composite. So be cautious on that, and be aware that you do want to be ready for that, because your patients will jump as well. I will get to the questions. I typically get to the questions toward the end, so don't hesitate to continue to write them in. I promise to answer as many, if not all, of the questions that I possibly can by the time we get to the end of it. Now let's take a look at fillers. Fillers are important because they improve the physical properties of the composite materials. They reduce the shrinkage of the composites when cured. They create the characteristics of your composite. Your characteristics of your composite are a result of your filler material, the surface of the material, the size, shape, load, modifiers, and size distribution. And we're using materials currently such as strontium glass, barium glass, quartz, borosilicate glass, ceramics, silica, polymerized resin, etc. There's quite a wide assortment and range that's being used today. The composites that we use, of course, are classified by their shape and size, irregular or spherical in shape. And what we know is that sphericals are easier to place into the matrix by the manufacturer when the composites are being created. The smaller particles are added to larger, as in less resin is then used, and if there's less resin used, there's less shrinkage when, of course, it's in the proper distribution. Categories that we are all very familiar with nowadays, of course, are the microfills, the hybrids, the microhybrids, the nanofill, and the nanohybrid composites. If you look at the linear graph at the top of this diagram, you can see how we're going from the macrofills on the left-hand side down to the nanofills on the right-hand side. And the particle size in microns is what is the characteristics. The lower chart will show you pictorially what the overall particle size will be in contrast. So in the middle column of the examples of dental composite classifications based on the filler particle size, you can see that the megafill isn't shown because it's too large for the schematic. Then you have the macrofills, which are rather large, and the midfills and the minifills, the microfills, which are very, very small in the pixelation, and of course the nanofills, which can't be shown in this diagrammatic area. Characteristics that we know about and how these materials work are we have to look at the coefficient of thermal expansion, the water absorption, the surface texture, radial opacity of our composites, the modulus of elasticity, and of course the solubility. Internal stress is created every time we polymerize a composite. That's very, very important to understand. As the composite cures, it shrinks. That's the polymerization shrinkage that occurs. And as the polymerization shrinkage occurs in the tooth, it can pull the adhesive and the composite away from the preparation walls. This is one of the very, very challenging things, is internal stress. And this internal stress is becoming more and more apparent in a lot of research that's going on right now. You can reduce this internal stress by incrementally placing your composites in 2 millimeter or less increments, or if you're using regular composite types or bulk fills, up to 4 millimeters. You can also reduce this stress by using stress-breaking liners such as filled dental adhesives or resin-modified glass ionomer adhesives like Riva Bond LC by SDI. It's one of my favorite stress-breaking, stress-relieving adhesive materials in my office. It's pretty much one of my go-to materials. Composite selection, of course, is going to be looking at several different things when you're placing or you're using it. You're going to look at the strength of the restoration, the wear pattern, the ability of the color to be true to the surrounding surfaces. Placement characteristics, is it sticky or tacky, or are you able to mold and sculpt it into the preparation nicely? Can you use it to combine with opaquers and tints? And in our aesthetic world, we definitely need to master and learn how to work with these various opaquers and tints. Ease of placement and shaping comes into play, along with, of course, polishing characteristics and color stability. Color stability is something we'll talk about in a little while. It's becoming more and more of an issue because of the water take-up of a lot of our composite materials, so we need to look at that very, very closely. The advances in the microfunctional composites and the novel nanostructures are very important, because we've been able to, through the science and technology, been able to tailor with microstructural design the type of internal filler particle creation and architecture in our composites, which helps us create new classes of composite materials with remarkably improved properties. The nanotechnology that is now able to be used and incorporated into just about every composite system out there improves the light scattering. It enables excellent translucency in opalescence. The nanotechnology improves the wear resistance, gives us a high gloss with finishing and polishing, and of course, very important based on that is it reduces biofilm buildup. A rough surface is going to very easily collect the bacterium on it very, very easily. So the more highly polished your material is, the easier it's going to be able to resist this biofilm buildup, which is really very something else, very important. The next section of the presentation, it will focus on a material which I believe you'll want to take a closer look at in your day-to-day work. I read this statement because this is the first low shrinkage, low toxicity composite that you can work with both in the anterior and the posterior region that is compatible with your regular adhesive system that you use every day. And it's important to understand that you don't need any additional special bonding adhesives in your practice. If you're using a particular one that you like, you can use it with this material, and that makes this very remarkable to me. And the material that we're going to be talking about is the nanodimer technology found in the product Endurance by Septidon. This is a very unique product. It has created with a quote-unquote new chemistry, which provides outstanding physical properties and great aesthetics. Now, the word new is included in here just because it probably might be new to you, but this technology and product has been around for quite some time, but for some reason, I only recently noticed it in the recent past. And as I look at it closer, I don't understand why I haven't really paid attention to this before this time period. As I continue to work with it, I find its benefit in use in my office to be more and more remarkable. It's a breakthrough resin that is a mixture of three various monomers, the DDC-DMA, the EDP-ADMA, and the UDMA, in a remarkably unique and innovative combination. Remember, we were talking about earlier about how the chemistry of our resins and our fillers are so important as to how our composites will work. Well, this combination does things in very, very interesting ways in the restorative process. The most composites, as illustrated in the lower part of the diagram, will polymerize in a single phase, which creates an incredible stress, as we were talking about earlier, on the material and the tooth surface interface. Endurance, because of the unique dimer technology resin factor, this polymerization occurs in a phase separation manner, which reduces significantly the volumetric shrinkage and the shrinkage stress. This is really very smart technology. So in and of itself, this material will help to reduce some of the challenges that we are facing with our composite curing mechanisms. So this has been very, very useful in my office. The dimer technology in the Endurance will create lower volumetric shrinkage with incredibly great radial opacity, extraordinarily good compressive strength of 319 megapascals, and again, compatible with all your bonding agents. And it has a high intraoral monomer conversion rate of 75%. Now, this is very, very important. We're going to look at this a little bit more closely because this optimizes the physical and the mechanical properties, and also is very much more biocompatible, because one of the biggest challenges is when you polymerize and if you have the conversion of your resins to a very high state, you will have a lot of failure of the composite. Noted here on the chart in the box area, note that the high volumetric shrinkage of most of the materials in that box, while composite sciences try to increase the conversion ratio of the materials to reduce the amount of unreacted monomer, this, however, creates a remarkable increase in volumetric shrinkage and shrinkage stress in our conventional composites. Endurance, down at the lower right of the chart, is able to convert more monomer and keep stresses significantly reduced due to the phase separation curing that we just discussed a few moments ago. So we have some interesting properties here that, in my work every single day, certainly makes this a material of choice from an aesthetic point of view and from a functional point of view when we're working at it. This material, it gives us increased biocompatibility. In my work, biocompatibility is extraordinarily important, and this high monomer conversion rate is part of it. Less free monomers are available, and unpolymerized monomer in there. It minimizes the risk of any tissue response, because you do get tissue response, unfortunately, with some of our materials. And if you can reduce that by the tying up of more and more of the monomers into polymers, that's going to make things very, very nice there. Very good conversion, as illustrated here in the chart. And its filler is very unique as well. It has this combination of fillers. We talked about earlier about how the fillers are an important part of the composite. Well, here we see that the filler combination is such that it enhances the wear, the color, the polish, and other properties that we look for in our restorative materials. The nice part about this is it's a system that comes in a variety of shades, including a universal opaque, an incisal, and a bleach white. It's extremely polishable for natural-looking restorations. I had a patient in today who chipped off front tooth number 8 at the incisal edge, and she was really, really troubled by it. The interesting part is she had her lower teeth veneered by another dentist many years back, and the veneers moved over onto the lingual, and so you had a lot of ceramic on the lower restorations. And so when she'd go into excursions, she, of course, would rub on the upper teeth, and what's going to give? The composite or the ceramic? In this situation, the composite certainly gave way. So we used endurance today with this particular patient, and by the time we were done, because of the high polishability and the color, I was able to get and balance the occlusion very, very nicely to reduce the excessive forces and get a color match that she couldn't tell difference between her own teeth and the restoration that I put in there. So you're going to get really excellent relations there. This wart absorption and solubility is really interesting, because one of the things at the AADR just past March in Charlotte, North Carolina, a poster was presented there that compared many different of the popular composites that you and I know and use in there. And one of the challenges that it talked about was the bottom line that discoloration is still one of the biggest long-term problems of our restorations. The study measured all of the various composites such as Estelite and Filtech and Herculite and Grandioso and etc. and TPH, and it found that endurance had the least likely stain capability. So that's because it will not absorb water very, very easily. It is very, very low solubility and absorption of water, so it really helps in that, and I find that in my restorations working with Endurance, it sure makes my life that much easier because I can count on that. Compressive strength is, of course, outstanding as well, and the flexural strength. This is important because you want your maximum stress to be at least 80 megapascals, and you can see most every composite in the chart is 80 or greater, and Endurance is right in that midsection where you would want it to be. That means it's able to have good flexural strength, and it's going to reduce the overall fracture of the composite quite nicely. And wear resistance, again, quite nice. It's toward the lower end of the spectrum of the various composites. And again, all of these various composites were the same types that were looked at in the AADR study a couple of weeks back. And again, some examples of the use of Endurance with closing diastema, anterior work, building broken edges of teeth. Really very, very fine results, extraordinary polish, and very, very good durability for both your posterior and your anterior procedure. So I've had really nice results with it, and I think you will as well. Interestingly enough, also, they've created Cristal, which is used for class 3, 4, and 5 restorations. It has an increased translucency, so for those situations in which you need that much more, you can use Cristal in this. Very, very hydrophobic, again, to help to maintain and keep your color stability with the same kind of basic principles of low volumetric shrinkage, high internal monomer conversion, and excellent radiopacity, and compatible, again, with all the various composite bonding agents that are out there. And again, this is an example of the shades that Cristal has available. And again, this has made a very nice improvement in my aesthetic work in the office, because now I've got a material that is strong, that's going to be color stable, and that has great translucency in those areas where I want it to give a more lifelike and natural appearance on things. Very easy to use. It's highly thixotropic because what happens here, as you work with it, it becomes more pliable. You can mold it. You can flow it into places. You can really tease it into the shapes and ways that you want it. Very, very lovely, very, very easy material for me to use, and I think you'll find the same thing as well. And finally, I want you to understand that this material comes with a guarantee. They have basically indicated that if it has a 10-year warranty on it, that they're so confident in what you're going to work with this material that if there's failure, they will purchase it back and reimburse you for the material. So that's something that no other company is really doing at this point in time, and Septidon has really stepped up to the plate, not only in bringing together excuse me, a great science with the fillers and the monomers, but also the high conversion factor with its composites and the low water absorption. So it's really very, very good.